I find thin films to be a cool topic. As a teacher, I like that you kind of have to get all these little pieces and put them together. I like that there's kind of a logical step. Hopefully you like them. Hopefully you're okay with them. They've got neat applications in the real world. Kind of like this one, maybe a silly one. If you put a coating on the lenses of glasses, you can engineer it so that that coating reflects a particular color. I'm always going to start off with a little doodle, just sort of a rough thing. I'm not going to use any fancy tools and make nice rectangles. So pretend that's a rectangle. That's going to be the lens of the glasses. And that says, they're out of order, but it says that the lens has an index of 1.4. On top of that, I'm going to draw it to the left is this thin film. So my scale is no good. This film is the thin film. It's quite thin. It's got an index of 1.2. The light's going to come from this left side. The index over here, it's in air, so that's an index of 1. There's lots of bundles of light that are involved when we work through our thin films. The two most important ones are the bundle of light that goes in and bounces off the film itself. I'm going to call that bundle of light number 1. And the second bundle of light is the one that goes into the film and bounces off the material behind and comes out to your eyeball. Your eyeball would be over here somewhere. There are other bundles of light, maybe the one that goes into the lens and bounces off the back of the lens, but they don't have an impact on the thin film reflection. So we're just going to focus on those two. I'm drawing them on an angle like that just so we can see them better, but really they'd be right on top of each other, kind of collinear. The light going straight in, bundle 1 coming straight back off the film, bundle 2 coming straight back off, in this case, the lens. So I don't forget later, what I like to do right off the bat is find that lambda in the film. So when the light from the air enters the film, it slows down in this case since it's entering a larger N, and the wavelength actually shrinks a little bit. We can get the new wavelength by taking the wavelength in air and dividing by the index of the film. I don't care about the light that goes into the actual material, in this case the lenses, so I don't really need to use the 1.4. The math on this one, unless I goofed, I'm getting 450 nanometers is the wavelength of the light when it's in the film. The next step in the process is to consider the reflecting. Bundle of light number 1 was in air, reflected off the film, so it reflected off a larger N. Bundle of light number 2 was in the film, which happens to, in this case, it's an index of 1.2, and it bounced off the lens, which was an index of 1.4. So it also reflected off a larger N. If this is all that was going on, these two bundles of light would be in phase with each other. Now, the logic step, we have to look at the question. Does the question ask for constructive interference or destructive interference? Reading through this question, it says there's a bright reflection. Bright reflection is the vocabulary, one of the vocabularies, for constructive interference. They're already kind of in phase because of the reflecting, but bundle of light number 2 traveled farther, t on the way in and t on the way out. So it traveled 2t farther. We want them to be in phase. They're already kind of in phase, so that extra distance that bundle 2 travels has to be a multiple of the wavelength. It could be lambda. What the case we're going to work through is 2t must be 1 lambda prime. It could work out that it's 2 lambda prime or 3 lambda prime, but the thin film interference tapers off dramatically, so the only thickness we worry about is the full lambda case. Flipping the half over, oops. Since they're in phase because they're reflecting and we want them to stay in phase, the 2t must be a lambda prime, which means t must be half of lambda prime. For the numbers in this question, the lambda prime was 450, so t is half of that, 225. There are different permutations we can go through, whether the ends are kind of in order. In this case, the ends went from small to medium to large. therefore the reflected rays were in phase. Maybe I ask a question where that happens and it's a canceling, then the extra distance would only be half a wavelength. We'll work through